Hello everyone, welcome back to our discussion of river geomorphology and rivers in the context of geography. We're going to continue on our discussion talking about antecedent streams. So a lot of times rivers can be exceptionally old and they can be older than the geologic events that are around them. Often when you have a river that's flowing, and then you have some sort of geologic event that causes uplift or compression or deformation of some kind, then that river still wants to maintain its constant slope and will carve into that ridgeline that forms as a result of that geologic event. And that steep gorge there can be seen in several different places. For example, we have the Delaware River Gap is a great example of this in northwest New Jersey, where you have this stream that was then had an uplift event that formed this mountain range, and the stream has since carved into it, forming this deep gorge. So our random phrase for this week is the dogs dance on Thursdays. The dogs dance on Thursdays. Next, we're going to be talking about the Strahl stream order. So the Strahl stream order is a way of categorizing a stream based off of how many tributaries run into it. And so the way that we do this is that we first assign all of the endpoints of the stream at the farthest reaches of the watershed a value of 1. And whenever you have numbers that combine with the same number, you increase that value by 1. So for example, you have a 1 stream and another 1 stream that combine and form a second order stream, 2. And then here we have another second order stream hitting a second order stream and making a third order stream. But here we have a first order stream hitting a third order stream, and that stream will still maintain its third order classification and will continue being a third order stream all the way until it hits another third order stream and becomes a fourth order stream. So we can categorize all streams in the world this way, and the Amazon River has the highest stream order in the world. It's an order of 12. So you can imagine just how many tributaries the Amazon River has. And we can look at the Strahl stream orders for all of the United States, the Mississippi River being our largest stream order of 7. And as you get to more and more complex drainage networks, you can have larger stream orders. And it's a good way of categorizing a stream, and a lot of government legislation dictates different regulations based off of the Strahl stream order like this. So next, let's talk about delta formations. Deltas are important features at the mouths of rivers, and let's hear about how they form.
The world is divided into 2 kinds of people, those with innie belly buttons and those with outies. Rivers also have innies and outies, not belly buttons but mouths. Where rivers flow into the sea, the land either pokes out or bends inward. But rivers don't have umbilical cords, so why do they have innies and outies? Well, coasts are the front lines between 2 opposing forces, land and water. In order for the ocean to invade the land, sea level either has to come up or the land has to sink down or be eroded away. And in order for the land to advance into the ocean, sea level either has to drop or the land has to build or be lifted up. Obviously, if sea level drops and then rises back again, there's no net gain on either side, but things get more complicated when a river joins the battle. For example, during the last ice age, sea levels fell by over 120 meters, and rivers cut deeper and deeper valleys to reach the falling seas. Then, about 18,000 years ago, warming temperatures began to melt the ice, and the now rising seas flooded river valleys around the world, creating giant estuaries and giving us the innie-riddled coastlines we have today. But when the steady landward march of the seas finally began to slow about 7,000 years ago, the coastlines around the mouths of some rivers began to gain back some ground. The key factor was the sediments that rivers drop as their currents slow at the entrance to the sea. Where the sediment supply was big enough and the ocean was calm enough, the dropped dirt piled up, eventually forming new land that both lengthened the river and divided it in two. Dirt would continue to drop out and build up at the mouths of both channels, splitting the river again and again and again, creating a new lobe of land advancing slowly into the sea. Thus, the world's great outie river mouths, the fertile deltas like the Nile and the Yangtze that have helped foster human civilization since its birth, all came into being at just about the same time. The same can't be said for all of the world's outie belly buttons. What can be said, though, is that innies and outies, for both rivers and people, are a small record of how we came to be.
Yeah, so deltas are representative of how much oceans versus how much the land is dominating the system. And we can classify the delta based off of which one is more dominant. So we have deltas that form as you have sediment that comes in and gets deposited, and as that deposition occurs, you have the formations of islands and smaller channel networks as you have deposition occurring. And so we can classify the delta based off of whether it's wave dominated, river dominated, or tide dominated, or a combination of the three. So for example, the Mississippi River Delta is very river dominated, which means that it has a lot of sediment that's flowing out of the Mississippi River, and it doesn't have that strong of tides or waves to wash that sediment away. And so it has this long arm, sometimes called the chicken foot, that extends out from the coastline as you have more deposition occurring and depositing sediment further and further out to sea. Instead, we can also have a wave-dominated system, such as the Sao Francisco Delta, and this is where you have powerful currents and waves that wash away the sediment like you have in the Mississippi River, and instead you have a relatively straight coastline where the river comes in. That's sometimes also called a cup-sate river delta. And then in between those two, we can have a lobate river delta, where the river kind of extends out further from the other shoreline, but still that it doesn't have these kind of long tendrils and is still kind of cut off by the wave action. And then lastly, we can have tide-dominated river deltas. And those form when you have a really strong tidal current that flows in and out of the river delta system, and as a result you have a bunch of these islands start to form, like we saw in the video and this example here with the Fly River Delta. And so you have sediment being deposited, forming a new island, and being shaped by the flow of the tides. And so those are the different types of deltas that we can have. Next, let's talk about terrace formation. So terraces are big parts of the geomorphic impact of rivers. You can see some examples of terraced river terraces here. So terraces are these flat areas above a river that represent the historic river floodplain. And so the terrace formation forms through three different processes. First, you have some kind of uplift or sea level change that causes the height of this river to be relatively higher than its base at the ocean. And so when you have that increased height, then you have more energy, and then the river will then next incise into the floodplain. So step 2 is incision. After uplift, then you have the energy to incise down, and then eventually you're going to have meanders that develop, and you're going to have that river widen, forming a new floodplain. So what's left behind is just that terraced surface and the new river floodplain that represents that equilibrium point with the new sea level. You can see a model simulation of that here, where this river is moving back and forth, widening its valley, and then it eventually experiences some amount of uplift or sea level change, and you can see that here then it starts to incise, and then it'll form this new terrace surface as it widens that new floodplain area. So next, let's talk about different channel features. These are interesting things that happen within the channel of a river. The first one is a nick point. So a nick point is a sudden drop in the elevation of a riverbed. And often you'll have a waterfall associated with it, like Niagara Falls here. And so nick points form and they migrate upstream as a response to changes in the base flow level. So for example, if you have a fall in sea level, then that signal takes some time to propagate upstream. And you'll have, for example, this normal base level of the flow or the sea level that then drops, and then erosion occurs from the ocean inland and will slowly migrate back upstream and erode away. And so waterfalls will often move upstream. Niagara Falls not an exception, and will eventually hit the lake. The next channel feature that we're going to talk about are hydraulic jumps, also known as holes by whitewater rafters and kayakers alike. So hydraulic jumps are whenever you have this fast-flowing water that leads into this recirculating water here. You can see that here as well when you have this fast-flowing water coming down and then getting covered by this recirculating water. So what's going on here is oftentimes you can have some sort of break in the slope of the river, sometimes caused by a rock. And so the river flows over that, and then that change in slope causes that water to accelerate, and that flow goes supercritical. And then as it then slows, as it hits the new slope, then it slows down and goes into subcritical flow, and will then form this hole where you have recirculation occurring. So what do I mean by supercritical and subcritical? So we can define this term using the Freud number. So subcritical flow is slow flowing water where the Freud number is less than 1, whereas supercritical flow is fast flowing water where the Freud number is greater than 1. And in supercritical flow, the waves do not propagate upstream. And instead, if you have some sort of disturbance, like you throw a rock into the river, the waves that form out from that rock ripple will not propagate upstream and will just be forced downstream instead. You can think about it too with this formula here. A supercritical flow where the Freud number is greater than 1, then you have the velocity of the stream dominating over the gravitational pull. And so the gravity that's going on doesn't allow those waves to propagate upstream. And then next, the channel feature that we have are eddies. So eddies are kind of like hydraulic jumps turned on their side. So whenever you have a stream that's widening, then you have flow that's coming in, and then you have this area that needs to be filled with water as well. And so as it does, you have part of this flow that comes in and will recirculate back and form this vortex type of flow here. You can see this water coming in, getting diverted into this widened area and circulating around. And this can form whenever you have a rock that's in the way or a widening stream. For example, when you have a rock here that impedes the flow, then you have this void space that needs to be filled with water, and it diverts this water from the main channel, and it recirculates and flows upstream behind the rock. And that line between that upstream flow and the faster flowing downstream flow is called an eddy line. And so you can still have that eddy line develop in a river that's widening. So you have this constricted flow here that comes down and then hits next to this void space caused by the river widening, and that water then circulates back upstream to fill that void space, and that eddy line forms between the two. So those are eddies, and they can form all throughout a river system, are very important for rafting as well as for fish communities that like to live in eddy systems. And so let's take a break from there, and we'll continue on talking about different river features as we continue in the next video. All right, I'll see you guys soon.